All right, everybody, this is it. Last chapter, last lesson. Buffers, titrations, KSP. This is chapter 17 in your book. We're talking about acids and bases still. It's just elaborating a little bit on stuff that they can do. So there's a bunch of your practice problems. They will be on mastering, so let's do this. All right, buffers. What's a buffer? A buffer system is an aqueous solution that contains a weak acid or base and the conjugate. So the whole idea of a buffer is that since there's some weak acid and some weak base, it will be able to take any incoming strong acid or strong base and essentially like take away their strongness. It will take that strong acid and make it into something weak, or take the strong base and make it into a weak base. And so when you add a strong acid or a strong base to a buffer system, the pH change becomes minimal because you've taken that strong acid or base instead of putting it into the water, and instead of putting it into water and having, if I add acid to water, the pH is going to go way down very quickly. Whereas if I add it to a buffer, that strong acid is now a weak acid and the pH is only going to change a little bit. And so by doing that, you can, change the way that your solution behaves to incoming acids and bases. That's what a buffer is. They are always written with the acid and the conjugate base. And the base is written with a cation as the salt. So it would have sodium or potassium or whatever in front of your base. But remember that this is essentially going to cause no change in the solution because it comes from a strong base, so we can ignore it. So anytime you see this, just ignore the cation. We don't need it. The only thing you have to worry about is the acid and essentially the anion, the conjugate base anion. So don't get confused when you see these. And how am I going to write this in a rice table? Where does the sodium go? Who cares? Leave it out. You don't need it. All right. I want you to look at these, think about what a buffer is, and go through and tell me which one is a buffer and which one is not, and maybe see if you can explain why. All right, so this first one, we have two acids, not a buffer. You need an acid and its conjugate base. B, all right, we have an acid and a base, so that's good. The problem is that nitric acid is strong. And so it's not going to work because we need a weak acid and its conjugate base, not a buffer. Okay, now we have HNO2 and NaCl. Okay, weak acid, hooray, that works. However, this is a salt, not a base, and not the conjugate. Nope. HNO2, weak acid. NaNO2, get rid of that guy. NO2 minus 1. Conjugate base, hooray. D is the only buffer solution because it's the only one that has the acid and its conjugate base, and the acid's weak. Okay. The Henderson-Hasselbalch equation is the easiest way to find the pH of an acid. You need to know the Ka. To find the pKa, it's the negative log of the Ka, just like it's the negative log of your H concentration. And then you're going to add the log of the base divided by the acid. So do that division first, then take the log, and then you're going to add it to the pKa. All right, let's look at number 2. Calculate the pH of a buffer solution that is 0.05 molar benzoic acid and 0.15 molar sodium benzoate. And we know that the Ka is 6.5 times 10 to the negative 5. So if I use this equation here, I need the negative log of the Ka plus the log. Okay, I need concentration of base over acid. Please make sure that you don't get these confused. This is the acid, this is the base. okay? Acid base. All right. So we need base over acid, so we're going to put 0.150 divided by 0.05. All right, and if we calculate this out, my pH is 4.67. Okay, because the log of that is 0.477. My pKa is 4.19. Add those together. Okay, that's how you do it, easy peasy. All right, you guys, try it. There it is, you guys. Just double check. Make sure you use the log button on your calculator. All right. An effective buffer, and by effective I mean one that is resistant to pH changes. You want to have close to an equal amount of acid and conjugate base so that they will balance each other out. You also want a high concentration. A lot of the times people will ask you about diluting a buffer and what that does to the pH. If you dilute a buffer, all you're doing is decreasing the acid concentration and the base concentration, but you do it like relative to one another, so you're not changing the concentration, you're diluting them both, and you're diluting them both by the same factor. So it doesn't change the pH, but it does dilute them, and so they are less capable, there's less there to buffer any sort of acid or base coming in. So they're not as good at regulating pH because they're diluted. But it actually does not change the pH because the ratio of acid to base stays the same. Okay, so that's what you want for an effective buffer. Equal amount of acid and base, and high in concentration is good. All right, titration. So with a titration, essentially you are trying to figure out an unknown concentration of acid or base. Usually it's acid, but it can be either way. And you do that by performing a neutralization reaction where you have an acid plus a base going to salt plus water. So the pH goes from, if you started out with just acid and then you add base as your titrant, you start with a low pH, you add the base and it goes up, 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 and then eventually you get to neutral pH. That's why it's a neutralization reaction. What we do is we say, okay, well, we know that once we reach that neutral point, my amount of acid is equal to my amount of base. So if I know the amount of base and I know the concentration, I can calculate the acid concentration with a simple calculation. So we add a solution of known concentration of base. We have to know what one of them are in a burette that's graduated. And we can measure the volume that we add. You add it little by little. You can use the stopcock to adjust how fast you add. You measure the volume of how much you titrate in, and then you calculate your unknown. That's how you solve a titration problem. All right, so we are going to use this equation, which we've basically used before, except we used to use 1s and 2s, but now we can say acid and base. So if you are doing titration and we need to know what the concentration of our unknown is, we're looking for M of A, and we have the rest of it. So our volume of acid is here, 25 milliliters. Our volume of base is here. There's my molarity of my base, and so I just solve. So MA is going to be equal to MBVB divided by VA. So we're going to say 0.1 molar times 32.5 mils divided by 25 mils was what I started with. The milliliters cancel, I end up with molar. And my concentration is 0.13 molar. It's as easy as that, guys. MAVA, MVBV. Try 5. Let me know what you get. There's the answer to 5. I had to change my liters to milliliters. But there it is. Easy. No sweat. So in lab, there's a couple ways that you can monitor a titration. One is with a pH meter, which we'll use. And it measures voltage, converts it to the concentration of hydrogen ions in solution. You end up with a sigmoidal curve, which just means it sort of makes this little S pattern where it rises. And then you get to a point where like all of a sudden it goes up really quick and then it kind of levels out again. At the equivalence point, which is sort of in between like the last point here and the first point here, it's kind of where it's straight up and down. That's your equivalence point. So you can read the pH and you'll find out what your volume is and also what the pH is at your equivalence point. It's not always 7. It will be 7 if you are doing a strong acid, strong base by titration, the pH will be 7. But no matter where that is, at your equivalence point, the moles of your acid is going to be equal to the moles of the base. And so then we can do our calculations and figure out the concentration from that. A strong titration is easier than a weak strong titration or weak titration. But the equivalence point is going to be at 7 if it's a strong titration. You can also use an indicator, which is usually a weak acid, that will change color when you get to a specific pH. So essentially what it is if I'm adding base, right? OMG, that's hideous. So if I'm adding base and I'm reacting with my strong acid and it reacts, and then I run out of strong acid, but I'm still adding base because I don't know I've run out, that first drop that you add that has no strong acid defined, it's going to find that weak acid indicator. And the idea is as soon as this reacts, it undergoes a color change and you can see it. So when we use phenolphthalein, it will turn pink. And the lighter the pink color, the better, because that means that you've only reacted a small amount. So you haven't over titrated. You haven't added too much extra. If you use an indicator, what you measure is the end point, which is different than the equivalence point, because the end point is actually the next drop after the equivalence point. But it's a good estimator, and you never really have trouble getting a decent value from an endpoint. It's just not the same as the equivalence point. It's like the next drop after your equivalence point is your endpoint, depending on how good you are at titrations. So it's a good estimator, and that color change is fun, so that's always good. If you titrate a strong, meaning a strong acid with a strong base, you're making water. It's a neutralization reaction, which I talked about, and we can find our pH, and it's pretty relatively easy. All right, so here's a big long problem. You have 25 mils of a 0.1 molar HCl solution, and you're going to titrate NaOH. What we're going to do is we're going to, after every step, find a new pH. There's a couple ways that we have to do this. Well, first, aside from A, you have to do a dilution, because every time we are adding NaOH, which is going to dilute my concentration of both the HCl and the NaOH. So I got to find my new concentrations after I mix them. Then I have to sort of make a rice table and do some calculations. Okay. So I have 25 mils of a 0.1 molar, and I need to know the initial pH. Well, if I haven't added any base yet, and I have a 0.1 molar HCl solution, that means that my hydrogen ion concentration is 0.1, right? Because it's strong. So I take negative log of 0.1 will be my pH. That's 1, my friends. So that's easy. All right, so let's do B. I have 25 mils of 0.1 HCl, and I'm adding 5 mils of NaOH, 0.1 molar. First I have to dilute, okay? So for my acid, I have M1 is 0.1 molar times my V1 is 25 mils. My V2 is my final volume, so my M2 is X, that's what I'm looking for. Final volume here is 30 mils. And then for the base, I have 0.1 molar times 5 mils times X times 30, because that's my total volume. And I get 0.083 and 0.017 molar. Okay, perfect. Okay, so I know that my H plus is going to react with my OH minus, and I'm forming water because it's strong, strong. So there's my reaction. I took out my counteranions that I don't need, and I'm going to say, okay, well, initially I have 0.083 and 0.017, and I don't care about water. So all of my, like, I got to find out which one's limiting, right? So OH minus is limiting because it's the least one. So I'm going to subtract from both of them, whichever one's the least. I run out of OH minus, and I find my new concentration of H plus because I've used some. And this is 0.066 molar. Okay, because I've used some of my 0.083 to make water. So now that's my H plus concentration. So I take negative log of 0.066 and I get 1.18. So I've gone up a little bit because I added base. And we're just going to keep doing this. For C, I still have 25 mils of acid, except now, what am I adding? 10 mils of 0.01 molar NaOH. I do my dilutions. 25 times 0.1 equals, now I have 35 milliliters times X. 10 times 0.1 equals 35 mils X, which gives me my new concentrations, right? I do 25 times 1 divided by 35, and I get 0.071 and 0.029. And again, that's what I have initially. I react all of, since I know like how much I have and how much is reacting, I just subtract. And I get 0.042 and I get 1.38 is my pH. There's no molar here. All right, so I put molar on that first pH, but I shouldn't have. This was pH. And this is 1.38. So I keep going up. That's my pH. All right. All right, for D, now we add 25. So I have 25 milliliters times 0.1 molar. 25 plus 25 is 50. So I got to find my new concentration of acid. And then base, we have 25 mils times 0.1 molar equals 50 mils X. Okay, well now I have 0.05 and 0.05 molar of both. This is my equivalence point, you guys. I have the same, so if I write my little reaction out here, it's 0.05, 0.05, minus 0.05, minus 0.05, 0, 0. My pH is 7, because that's my equivalence point. What happens when we go beyond the equivalence point? So this was D. Let's do E. So now I got, again, 25 times 0.1 equals, okay, so now I add 30 mils of my NaOH, so my, and then 30 times 0.1 equals 55. All right, So I make my table. And this is acid and this is base. You see the pattern? You just like keep doing the same thing. All right. Okay, well now I have less acid than I have base, so that's what I'm subtracting because that's the least amount. So this is 0, and I get 0.009. But that's my concentration of OH minus. So if I do negative log of 0.009, I'm going to get my POH, which is fine. But I asked for pH, so I subtract. And that's my pH, 11.95. And that's the whole thing. So that's how you do it. If you run out of everything, it's pH 7. And then once you're past that, then you are finding your OH concentration, and you just got to subtract. All right, you guys. I want you guys to try 7. Here is the answer for number 7, A, B, and C. This time we are adding acid to base, but they're both strong, so you do it the same way we did the other one. We have a before the equivalence point where you have leftover base, so you got to find the POH, then you find the pH. And then we have equivalence point, so the pH is just 7 because it's neutral. And then C, we are post-equivalence point where we've run out of base and now we just have acid left over, so we find the pH. Okay. All right, now that we did strong titrations, what about weak strong titrations? So if you have a weak acid and a strong base, that's usually what you have, or vice versa. Your pH at the equivalence point now is not 7 because it's not equally matched, right? So you're not going to meet at the middle. If the acid is strong, the pH is going to be below 7 because the acid will kind of win out. If the base is strong, the equivalence point will be above 7. All right, because the base is more influential over your pH. So we would do this the same way we do a complex buffer problem, which I didn't make you do because I'm so nice. And so we're just going to do it here. These are just kind of a bunch of rice tables along with a Henderson-Hasselbalch, but we also still need to do our dilutions, so we can't forget those. So let's look. So this part is the same as before. We still use our MAVA equals MBVB equation. It doesn't matter. So we can easily find the molarity at the equivalence point. So you guys can pause and do this one. All right, here it is, 0.21 molar. That's it, same way you did it last time. Okay. Now we have to work through this big monstrosity of a problem. Initially, we need to find the pH. And before, the last one, we could just say, oh, if it's 0.1 molar, the pH is just going to be negative log of 0.1 molar, but this time it's not because it's weak. And so we have to use the Ka in order to calculate it. So for this first one, initial pH, we got to make a little rice table. All right, and we have 0.1 molar. This we don't care about. We don't have any of that. Okay, my Ka is small. That's an 8. And so now we solve. We can drop this because it's small. And so we get x is equal to 0.0042, and negative log of that is going to give us the pH because we found our concentration of acid, so it's 2.37. Okay, easy, right? No biggie. Okay, so now with B, Now we are adding 5 milliliters of my strong acid. So now we have to do a reaction. So this is a little bit different than a rice table because we're not just throwing, it's a little bit different than our usual rice tables because we're not just throwing it into water. We're actually running this reaction. So first we need to do our dilutions, just like we did last time. Acid base. So I start my acid, I start out with 0.1 molar times 25 mils. I add 5 milliliters of base, so my total is 30 mils, and that's what I don't know. Okay, I have 0.083 and 0.017. All right, so now I can make my little reaction happen here. So this is a reaction, so it's no longer an equilibrium because it's just going to happen. So we form water, right? And then we're going to form our anion, the conjugate base to my acid. We essentially make a buffer because we'll have some base and some acid. So I'm going to have my initial concentrations is what I calculated in my dilutions. I don't have any of that yet. Okay, so now I have to make these two react. So I have to subtract 0.017 by the limiting reactant, and then I add it over here. Okay, so now I am left with no OH minus, right? We have 0 here. I have this much of my acid, my weak acid, and I have this much of my conjugate base. So I have some weak acid and some of its conjugate. That's a buffer, right? So I can use the Henderson-Hasselbalch equation to just plug those values in and calculate my pH, because I also have the pKa, or the Ka at least. So remember, I'm going to do pH is equal to pKa plus the log of my concentration of base over my concentration of acid. Just make sure you keep your numbers straight. So I got pH negative log of 1.8 times 10 to the minus 4 plus the log of my 0.017 over 0. This should be that 0.066. All right, if you calculate that, you get a pH of 3.15. You want to make sure it has gone up because we are adding base, so we should start to see an increase in our pH, and we do. All right, you guys. So I want you to try C and D. You can do those ones just like I did B and see what you get for pHs. Okay, guys. Here is the solution. So we keep going up in pH. Make sure this all makes sense to you. We're just working our way as we go. Just make sure you do your dilution so that those concentrations will change every time. In D, we're like quickly approaching our equilibrium, our equivalence point. And so the next one we're going to do a little differently. So there's C and D. All right, so here's E. Now we are at our equivalence point. We know that because if we do our dilutions, we're going to end up with the same amount of our acid and base in here. Okay, so I have 0.05. All right, so I'm going to go ahead and make my rice table. Okay, so I'm going to put these in. So at the equivalence point, we don't have any of our weak acid and strong base left because that's the whole point of this. But we do have weak base, and we have, that's it. So we need to make a second rice table, which is why this one is the most annoying one. So I'm going to throw this into another rice table, and this one I just throw it in water. So when you are at equivalence point, you need a second rice table with whoever is left. So that's what I'm going to do here. and I'm going to throw it in water, and now we have our equilibrium back. We form our conjugate acid and a strong base. Okay, so I have this. We don't care. 0, 0. Back to old school here, you guys. Okay. Remember we talked about this relationship just like a teeny bit, and I was like, this will be useful later. Well, here's where it's useful. Because I have Ka, that's what I was given, but this is a base. And so when I am finding x here, I need to use the Kb. So I have to take 1 times 10 to the minus 14 and divide by my Ka to get my Kb. And it's 5.56 times 10 to the minus 11. Okay, so now I can solve for x. So when you solve, I get 1.67 times 10 to the minus 6. That is my concentration of OH minus. I take the negative log of that. I get 5.77, but that is my POH. So I need to take 14 minus 5.77, and I get 8.22. Okay, check your answer. You know that if it's strong, your pH is 7. Since I have a strong base, it should be higher than 7, and it is. Thank goodness. This is the most annoying case when it is at your equilibrium point. I keep saying that, at your equivalence point. Okay, there's one more scenario that I will show you. So the last possibility is to go past the equivalence point. So this is F. So we do our dilutions again. We always got to do this first, don't forget. 25 milliliters times 0.1 molar. Now I'm at 55 total milliliters because I've added 30 of my base. Acid, base. All right, so I have 0.045 molar and 0.054 molar. Okay, set up my table just like I did last time. Plus my conjugate base. Okay, fill this in, 45054, don't care, 0. Minus, okay, I gotta subtract the one that's the least. All right, this, my friends, this is a strong base. Therefore, we don't care about anybody else that's left. The weak base does not matter. We don't care about that weak base, so this doesn't matter. All that matters is this, and that is my OH minus concentration, which I can use to find my POH. Negative log of that is 2.04. Now I can find my pH because I can do 14 minus 2.04, and I don't have to do any other crazy math. Done. Now it's way high. So past your equivalence point, your strong base or strong acid, if that's what you're titrating in, is going to rule, and you just find out how much of that you have left. So that's just a subtraction, and then go from there to find your POH and your pH. And that is a weak strong titration. So you have before your equivalence point, you're going to use the Henderson-Hasselbalch equation. At the equivalence point, you're going to do the 2 rice table method and figure out your pH there, and then afterwards, all you care about is whoever strong is left. Okay. Here you are. I want you to try A through F for this one. So here's A through D. The first one is just an MAVA, MBVB to figure out what your equivalence point is. So we're looking for V2. Our equivalence point is 20 mils. So once we add 20 mils, that's when we know we're at our equivalence point. Part B is before our titration, before I add anything. I just have my weak acid in water. So that's old school, throw it in water, do your rice table, use the Ka and find your pH. So you get 2.17. Your first addition of your base, you do your dilution, you figure out how much acid and base you have, weak acid and weak base you have left, and you do the Henderson-Hasselbalch equation and figure out your new pH. Okay. D, I want to just point out because we're going to need this for labs, so you want to remember it. We are at half of our titration volume. We're at 10, which is half of 20. So we're half equivalence point here, okay? Half equivalence point. That's a big deal because when we are at half equivalence point, what that means is I have equal amount weak acid to weak base. When I have an equal amount of weak acid to weak base, because I've taken half of my weak acid and turned it into weak base, now my pH is equal to the pKa. So my pH is equal to the pKa, and I can find what my pKa is at my half equivalence point. So if I don't know what my pKa is, I just go, okay, I'm going to look at my graph that I've made in my lab, and I'm going to go to half my equivalence point. So if it's 20, I'm going to go to 10, and I'm going to read what the pH there is. That is your pKa. So at half your equivalence point, your pH is equal to your pKa. That's how you're going to find your Ka from your lab this week. Easy peasy. So here's the rest of it. Here's my equivalence point. So I didn't even do the first rice table because I know that my acid and my base are going to cancel out. And I started with no NO2, so if I'm canceling those out because I'm subtracting 0.067 from them, then I have to be adding 0.067 to the other side. So I just went ahead, assumed this, and ran with it with my second rice table. You can always make two, but I just was like, whatever, I'll make one. I had to find my Kb. I used this relationship, find my Kb, plug it in, find my pOH, and then I found my pH. And then the last one, I didn't care how much conjugate base I had. Doesn't matter. I just rolled with the OH minus concentration. And then I got my pOH, and then I got my pH. Okay, that's a titration. The last thing we're going to do is KSP. KSP throws everybody off for some reason, but they're actually really easy. All it's calculating is when you have a solid that doesn't appear to go into solution, so it stays a solid, it's insoluble. It forms a solid at the bottom, it sits there, does nothing. There always is like a teeny bit that does dissolve, you just can't tell. And so we can determine how much of it is in solution, even if we can't see it. We can calculate how much is in there, and it's really, really small. So KSP expressions, we're going to start with a solid, and then we just have to break it up into our ions. And these are aqueous. That's it. That's my balanced equation. So for A, my KSP, it's just a K. There's no denominator because calcium carbonate is a solid. Silver iodide, that's a solid. That breaks up into silver plus 1, aqueous, plus iodine minus 1, aqueous. PbCl2, solid. So I have lead, 2 plus, aqueous, plus, there are 2 chlorines, you guys. I gotta balance it out. KSP, forget that 2. I need it because of this 2, because of this 2. All right, that's it. That's your balance equation and your KSP expressions. You just break up the ions. If you need to review charges, go back and review charges, but that's it. Okay, so when you translate these problems, here's the thing. The word solubility in our rice tables is X. We know what X is. We've been doing X forever. So this is saying the X of copper iodide is 2 times 10 to the minus 6 molar. What is the KSP for copper iodide? So first, we write our expression. We write our balanced chemical equation. Copper iodide solid breaks into copper 1 aqueous plus I minus aqueous. My KSP is going to be copper plus times I minus. I'm going to make my rice table under here. I have 0 to begin with. We throw it into water. We have a plus X, X, X. So KSP is equal to X squared. You guys, we know X. They gave us X. The solubility is X. That's it. You square that number. No units. KSP. There it is. That's it. It does get more complex in the next one because now you have a 2x involved, but I think you can handle it. Pause and see what you can do with the next one. There it is. This time we had to do 2x, and don't forget to square it. So you get 4x cubed. Then just plug in x because we were told that the solubility is x, is 1.43 times 10 to the 2. Just throw it in. There's my KSP. So that's going from knowing the solubility to finding KSP. Now we have to go the other way, where we know the KSP and we have to find x. So again, we write chemical equation. Gotta balance it. KSP is going to be calcium 2 plus. Okay. Don't care. 0, 0 plus x plus 2x. X plus 2x. Okay, we know what the KSP is. So I'm going to move over here and I'm going to do 3.5 times 10 to the minus 11 is equal to x times 2x squared. And we know that that's 4x to the third. So we divide this by 4, take the cubed root, and we get x is equal to, because that's what we're looking for, 2.06 times 10 to the minus 4. So divide this number by 4, take the cubed root, and that's what you get. Don't forget your unit. All right, next one's your turn. There's 15, 1.83 times 10 to the minus 2. These are not all that hard to calculate. Okay. You know what? I'm going to stop there. That's it. That's all I want you to do. We're done at 15. Make sure you know how to do those. We are done. We're like really done, you guys. That's the last one. So I will see you on Tuesday.